Good morning, everyone. So today we are going to start the second day of our workshop. And so we have the pleasure to have here Pedro Vieira da Cunha from, he's a postdoc now in University of Aveiro, and he's going to start his short course for us about light rings and their topological charges. So thank you.
Thank you very much. And so it's again a pleasure for me to be here, and thank you for being so early in the morning. So this is a short course on light rings and their topological charges. So this is the objective of this short course is to give some more details about some of these techniques where you can associate a topological charge to light rings. So Carlos Herdeiro already gave some an introduction to the topic, and now my objective now is to expand on this. So I'm going to mention several works throughout this short course, done in collaboration with Carlos Herdeiro, Eugene Radu, also Emmanuel Alberti, and Nico Sanchez Gual. This is kind of a motivation for this within a broader question is what is the nature of astrophysical black holes? And in particular, are they really described by the Kerr solution? Or could there be models beyond Kerr that could mimic Kerr and its phenomenology? So that's kind of an overall picture. This comes in the context of new experiments in strong gravity, quite recent, both in gravitational wave sector with LIGO and Virgo, and also with the observation of the shadow image of the black hole by the EHT collaboration quite recently. Both of these channels have opened a new window into the strong gravity regime. And critically, both of these observations, they are connected to a special type of bound orbits, which are called the light rings, null orbits called the light rings. So, kind of an overview and the plan for this short course, I'm first going to discuss why these light rings are relevant for observations. And then I'm going to introduce the topological charge of critical points, not only associated with light rings, but on more general terms. On that, I'm going to do it on the blackboard, so you can see more carefully the details of this. And then I'm going to focus a little bit and apply these techniques for light rings around horizonless compact objects, and hopefully end this short course with application about light rings around black holes, and also other applications as well. And so starting, why light rings are relevant for observations? Let me just first mention what a light ring is. So a light ring is a spatially closed circular null geodesic orbit. And in spherical symmetry, namely Schwarzschild, you have this more familiar concept of a photon sphere, where you have a clustering of these circular photon orbits in a sphere. But they are a collection of these more fundamental structures. And beyond Schwarzschild, they also exist around Kerr, and also some horizonless stars. This is known. So horizonless, they don't have an horizon. They are not a black hole. And light rings, they are connected with the shadow of a black hole. This is clear, for example, when you're in the scattering process around the Schwarzschild black hole. A light ray needs a certain impact parameter just large enough so that it can escape the gravitational grip of the black hole. And so it needs a certain impact parameter and to approach this circular photon orbit. And it's clear that it is connected with the absorption cross-section. Now, because of the time reversal symmetry for Schwarzschild, this is also the same, will determine the shadow edge of the black hole. Also, the light ring, it's also connected with, potentially with the signature of objects that have light rings and are not black holes. If you vibrate them, you can see some signature that are not connected with the horizon. So in this paper, by Cardoso and collaborators. They take, for example, a wormhole that has a light ring, and you make a perturbation, and they realize that initially it can vibrate like a black hole, although it doesn't have an horizon, but because the initial part of the waveform that you see is actually connected with the existence of a light ring and not an horizon. So in principle, objects like this that have a light ring could mimic the black hole ring down. So in this context, it is useful to introduce this concept of an ultra-compact object. So any object, regardless of being a black hole or not, that has a light ring, it is an ultra-compact object. And the motivation to consider these objects is that they are closely connected with these important astrophysical observables, so in the electromagnetic channel with the black hole shadow, and in the gravitational wave channel with the black hole ring down and quasi-normal modes. Although there are some subtleties where this connection is less clear, but this is just as a motivation. And the interest of considering these objects is because they can mimic, in principle, Kerr, precisely because they have light rings. So with this motivation, now I'm going to move to this discussion of topological charge, of critical points, and move to the whiteboard, where I can discuss this a little bit more in detail. Então, podia parar a partilha dos slides, que eu vou só agora escrever aí no quadro. Tá, obrigado. And so with that, let's start. So let's start with the simple case. You have Schwarzschild. You have the Schwarzschild case in standard coordinates T, R, theta, and phi. This is something all of you are familiar with, but still it's always good to start with something that we already know. So here, M is the black hole mass, and because you have spherical symmetry, you can restrict null geodesics to be analyzed only on the equatorial plane. So if you look at one-dimensional radial motion, you can write this equation for the radial motion of null geodesics. You have r dot squared. So r dot here is simply the derivative of the radial coordinate with respect to some affine parameter. Plus a potential V, which I'm going to say what it is in a moment, equal to E squared over J squared. So this term here you can interpret as a kind of a kinetic term, which is always positive. So it's kind of a kinetic energy. We have this potential V, which explicitly is this 1 minus 2m over r divided by r squared. And then this is equal to E. E is the energy of the photon with respect to infinity, with an observer at infinity, and J, the angular momentum of the photon, also regarding an observer at infinity. So this should be, so this term here, you can call it an impact parameter. If you now make a plot of this explicitly, so if you draw here 2m, the horizon of the Schwarzschild black hole, the plot looks something like this. It goes to 0 asymptotically. You have a maximum exactly at 3m, And now if you consider the scattering process of photons coming from infinity, so they come from all this direction to here, they have a certain impact parameter E over J. So imagine that they have an impact parameter which is smaller than this maximum. So something like this. Let me change the pen. So I have a photon that comes from infinity and has this value of E over J. So in this case, because the impact parameter is smaller than this maximum, there is a reflection and it goes back to infinity. If this impact parameter is larger than the maximum, then it will pass through this maximum and fall into the black hole. But if you choose your impact parameter just right, it will approach this maximum here. So this will correspond to a critical point. Critical point. And it will approach, and you guessed it, the light ring. So from this, it is clear.
Sorry,
Yes?
because V has the dimension of 1 over r squared. So r dot is dimensionless?
So this is not, sorry. So this is not phi, this is lambda. So it's some sort of affine parameter that has no dimensions in principle.
But still, you have something that has dimension. But I think there is a factor missing somewhere.
Well, it depends on how do you define this potential. In principle, I don't think so. So usually you can have GRR here, but you can, it depends on how you define this potential. So which factor do you think it's missing?
No, because I'm looking at, so you have r dot squared.
Yes.
So this has dimension of F of
So this has dimensions of length squared, right? So
Yeah.
V of r, you have 1 over r squared there. So 1 has the dimension of 1 over L squared. So maybe there's something that I'm not able to see. You see what I mean? Or?
Well, I think when I wrote this equation, I might have used some kind of normalization for the affine parameter. So there could be something from there. So this is correct, but you could indeed, I think I might have absorbed some term in the affine parameter. So it might have some dimensions.
Okay.
Okay,
Thank
so
you.
sorry, yeah, I think it might be right. Okay, so from this it is clear that, that the condition for the light ring is given by, so let me write it down, the light ring is given by the condition that the derivative of this potential is equal to 0. And that will lead to R equals 3m, if you do the calculation. And also from this setup, it should be clear that this light ring on Schwarzschild has to be unstable. And why is that? Because imagine that you are exactly at the light ring. If you make a small perturbation and you have the right impact parameter to be just there, you can fall to the left and get out or fall to the black hole. So it should be clear from this profile that the light ring is unstable.
So,
Okay.
Pedro, sorry to interrupt you, but can you try using the black
Yeah.
pencil?
If you
because-
cannot see it well, yeah, thank you.
Sorry.
Better? Okay. So you have here this potential V again, but not, let's write again now a certain 1D potential. But it's not Schwarzschild necessarily. but it's still a spherically symmetric spacetime. So you can write a one-dimensional potential. So you have an horizon here. So this is not Schwarzschild. And you have a certain potential, like so. And again, you have a light ring here at the top. This doesn't go to 0 immediately. This goes to 0 asymptotically. OK. Imagine now that you make some local deformation of your geometry. Can you create new light rings? I think it should be more or less clear that if you make a smooth enough deformation in a certain region, in such a way to deform this potential like this, but keeping the boundary conditions, then you form two new light rings. So light ring 2 and a light ring 3. I hope this is more or less clear. If you want to deform this curve, in order to create a minimum, you need also to create a local maximum. So you might wonder, is there some conservation law that you can apply generically? Especially, how can you generalize this in the spacetimes with less symmetries? This is only in the spherically symmetric case, so you can always reduce to a one-dimensional potential for the radial motion. But if you don't have these symmetries, can you still have some kind of a conservation law for light rings? That is the question that we are going to try to address. So let me a little bit clear about the assumptions that we can have for the spacetimes that we are going to consider in this short course. I'm going to write a couple of assumptions. For what I'm going to call an equilibrium spacetime. In particular, I'm going to consider a 3+1 spacetime manifold M, metric G, that is topologically simple.
So, Pedro, sorry to interrupt you again,
Yeah?
but people are asking for you to write just a little bit larger.
Okay.
Because it's...
Can you see, people are seeing in the Meet and in YouTube what you see there.
I was under the impression that the camera would be able to zoom. Is it possible?
If it zooms every line, I think it's going to be complicated.
I see, I see.
So, I mean,
I'm going to make the lateral...
a little bigger.
Okay, that's okay.
We'll try to zoom it better.
Okay, thank you.
Let us try to compromise both sides.
Sure, sure, of course, of course. So this is can be a black hole or not. It's better. Also, I'm going to assume stationarity axial symmetry and also asymptotic flatness. Also, there is a critical assumption of circularity. If you are not sure about what's the meaning of this, circularity will essentially imply, together with the other assumptions that we have here, that there will be a discrete symmetry between the T-phi coordinates. So there is this discrete symmetry. So I'm going to justify what these coordinates are in a moment, but just to motivate what circularity will imply afterwards. Also, you assume a certain smoothness of the metric. I'm going to assume at the moment only that the metric is at least metric is C1 smooth. Only at the moment. And finally, we are going to assume that our space-time satisfies causality. In particular, let me just mention that since I'm going to assume that the space-time is topologically simple, we don't have wormholes here. And if we have a black hole, it is only of a spherical topology. Okay. So if you have stationarity, this implies that you have a Killing vector field zeta. And for the axial symmetry, you have a Killing vector field eta. So if you combine the existence of the zeta plus eta together with asymptotic flatness, this will imply, that these Killing vector fields, they must commute. So this is a theorem by Carter. And then you can choose some coordinates. T phi that are adapted to these Killing symmetries. In particular, you can choose this zeta to be equal to this, to delta t, and eta to be delta phi. In addition, you have, if you assume a asymptotic flatness, together with circularity, this implies that there exists a two-space that is orthogonal to the space spanned by the Killing vectors. So let's call this space S. So essentially, this is saying that there is a discrete symmetry, T phi, minus t minus phi. So there is this discrete symmetry, like you have in curve, for example. So this assumption of circularity is non-trivial. It is implied in vacuum, but here it's an assumption. For our two-space S, we are going to choose some coordinate system. Let's call it R and theta, that can have this usual interpretation of spherical coordinates when you go very far away. So, and you can do this safely precisely because your space-time is topologically simple. If you have a wormhole, you have to be much more careful. Okay. And finally, you can assume causality as well. And this will imply that G phi phi is bigger or equal to 0. This will actually define the axis. Oh, okay, thank you.
So those are much better.
Okay. Yeah, it's okay, so that was the assumptions and what they imply. Next, let's take the null geodesic flow, because in the end, you are going to analyze light rings, which are null geodesics. So for the null geodesic flow, you have this Hamiltonian, H, which is 1/2 of G mu nu, P nu equal to 0. So this P is the form momentum of the photon. And I'm going to choose a parameterization where the forward velocity is essentially equal to the momentum. Then because you have stationarity, this implies that the PT component of your momentum is a constant. Let's call it minus E. It's a constant of geodesic motion. This has the interpretation of energy of the photon with respect to an observer at infinity because of axial symmetry. You have also P phi is a constant. Let's call it J. So it's the angular momentum with respect to infinity, which is also a constant. Now, this is a sum over all coordinates. But because you have this orthogonal to space, S with respect to the space spanned by the Killing vector fields, you can actually decompose this sum naturally into two components. So let's do that. You can putting these two to the other side. So 2H is GRR, PR squared, G theta theta. So this term here has to be also positive. So this is a kinetic part, as before. And now you have this term here. So these A and B, they are a sum only on the T phi coordinates, so the coordinates that are connected with the Killing vector field. And this sum here, you can introduce a potential R and theta. So this will be a two-dimensional potential. If you are wondering what's the explicit form of this potential, it looks something like this. So we have U R theta. It looks like GTT E squared plus G phi phi J squared plus 2 minus E J G T phi. Now, the condition for the light ring, you don't want no motion on the R and theta coordinates. That's what you want. You want something that is circular. So It's a motion that is at each point tangent to the Killing vector fields. So you have no motion on the r and theta coordinate. That means that r dot is equal to 0, and theta dot is equal to 0. And this is going to be equivalent to having no motion. The radial component of the momentum is 0, and also p theta is 0. But this is not enough. This is kind of saying that the velocity is 0. You also want the acceleration to be 0. So you need this, and pr dot equal to 0, and p theta dot equal to 0. Now, if you go to Hamilton's equation, you can write that p dot mu is minus the derivative of the Hamiltonian. This Hamiltonian here. And so explicitly, also taking into account this decomposition, you can write this explicitly as minus 1/2 of this potential u, the derivative of the potential, plus a term that will be 0 when you have no motion on the radial and theta coordinates. So let me just point out that this term here is going to be equal to 0 at the light ring. So at the light ring, you have this term, and you want everything to be equal to 0, because you don't want that the derivative of the momentum is 0. In addition, you have 2h, the Hamiltonian, so this is essentially the same thing as here. And now at the light ring, likewise, this term here will be 0. Because you have PR and P theta equal to 0. So what is the message here? That at the light ring, both the gradient of this potential u and the potential itself, they both must be 0. So let me write that down. So you have that a light ring implies that the gradient of the potential u is 0, and that your potential must be 0 at a given point, so at a light ring. A very simple exercise that you can consider is, for example, the Schwarzschild case, where this potential u explicitly, you can check it, is given by two m over r squared, e squared over 1 minus 2m squared minus 2j squared over r cubed Yeah, so it's given by this. So it is a nice exercise, a very simple exercise that you can do to check that if you take this potential and you compute the radial derivative of this potential and set it to 0, and also the derivative on the theta direction and set it to 0, and that you want to also enforce that the potential itself is equal to 0, then you get three equations that allows you to write that r is equal to 3m, theta is equal to pi over 2, and that j over e is 3 square root of 3m. So this is the light ring at Schwarzschild. So you can see explicitly in this case that your potential u, which is two-dimensional, will depend on E and J. So it depends on parameters of the photon. So can you construct some alternative that depends only on the metric? Yes? Yes. Yeah, you can ask the question while I'm erasing, yes. Ah, okay.
Thank you. So you said that in Schwarzschild, due to spherical symmetry, one has a photon sphere and not just a light ring. So why can't we recover all the light rings with different impact parameters? For example, we are only recovering the equatorial light ring on this formalism. Where are the other ones?
Well, in this way, you don't see the others explicitly. They are there, and you can appreciate that they are there precisely because you have spherical symmetry. You can always rotate the equatorial plane.
Yes, I understand that.
It's not apparent from this. So yeah. From the point of view of this potential, these other light rings, they are orbits that are not planar. So you cannot see them explicitly in this formalism. But they are there. But generically,
they are not planar? In what sense?
They are planar, but you cannot see it clearly from this formalism, because they are not. They don't exist at a constant theta. They exist at a constant radial coordinate, but not a constant theta. That is the only reason. Okay, but they are light rings and they are planar, of course. But it's just not clear from this. But thank you. Okay. So, can you construct a potential that has no E and J? First, you can make the observation that light rings must have J different from 0. So you might wonder why. So imagine that it was not the case. Imagine that you had light rings with J equals 0. So imagine that you have J equals 0 and E different from 0. That would imply, from the definition of the potential, that you had a potential U that was GTT E squared. So this GTT, it's essentially the lapse. So outside the horizon, this needs to be different than 0, so this can never be 0 at a light ring. If you have J equals to 0 and E equals to 0, it's the other possibility. This will lead to an unphysical light ring. Why unphysical? Because the energy measured by a local observer is not positive. So if you enforce that physical requirement, this is also not possible. So you would get an unphysical light ring. So this is just to justify that J must be different than 0 at a light ring. Now, since J at light ring must be different than 0, we can introduce the impact parameter sigma, which is the energy divided by J. So at a light ring, this never explodes. So U can be factorized in this following way. You can have, right, as minus J squared G phi phi divided by G squared d phi minus GTT, G phi phi. Sigma minus H plus, sigma minus H minus. So these H plus and H minus, they are going to be our new potentials. Let me just write it explicitly. So H plus minus, they also depend on R and theta, so they are two-dimensional potentials. They are explicitly minus GT phi plus minus square root of this D, G phi phi. So this D is essentially this term here. It is connected with the determinant of the metric in the T phi sector. And this needs to be larger than 0 outside the horizon and outside the axis. So in particular, this doesn't blow up outside the horizon or the axis. And because of causality, G phi phi must be positive and never 0 outside the axis. So this is different from 0 at the light rings. So let me just emphasize that this is precisely what we want, that we have introduced a two-dimensional potential that only depends on the metric, does not depend on impact parameters. They have been factored out in a way.
So how you can guarantee that this D is in general different than 0 outside the axis and the Killing horizon? So I know that at the axis and at the Killing horizon this is going to be 0, but can you guarantee that these two cases are the only cases where it's 0? So
I think so, yes. At the moment, I don't have a very good argument, but I thought deeply about this, and I think the answer is yes, although I think the answer is a little bit technical to show here. Okay. But we can discuss this afterwards, okay?
Yeah, sure. Thanks.
Okay. So what are the two conditions for the light ring? You have the potential U is equal to 0, and also that the gradient of U must be equal to 0. So if you want this potential U to be equal to 0, you have two options. Since this term here is different from 0, either you have sigma is equal to H plus or sigma is equal to H minus. So this implies that either H plus is equal to sigma or H minus is equal to sigma. Now, these two equations, they only restrict the value of sigma at the light ring. They do not actually determine the location of the light ring, only the impact parameter. The condition for the gradient of U to be 0 at the light ring, so also enforcing this equation at the same time, this will also lead to two possibilities. Either the gradient of H plus is equal to 0 if sigma is equal to H plus, or you have the gradient of H minus is equal to 0 if sigma is equal to H minus. Those are your two possibilities. So it's clear from this that you can write that the gradient of H plus minus is equal to 0 at the light ring. There are two separate conditions here. You have a plus and minus. They will typically be connected with different rotation senses of the light rings. So this is explicit in Kerr, where the light rings do not coincide depending on the rotation sense. So this gives you two equations, and each one will give you a separate light ring. In Schwarzschild, because you have a static spacetime, they coincide, these two equations. So let me just make the following drawing. Just for the Schwarzschild case, you can make a drawing of this potential to see how it looks like. So if you draw a radial coordinate here in the x-axis and a theta coordinate in the vertical axis, here at this point you have 2m is the horizon, and here you have infinity. Here is pi, here is theta, 0 for theta. These, and then you can draw lines with h plus minus constant. These will look something like this. You might recognize from this profile, so these are lines that have constant h. You have this point here, that if you recognize lines of contours, this is a point where the gradient of h plus minus doesn't matter because it's static, it's the same, equal to 0, and in particular it is a saddle point. So it is a saddle So in a way, these standard light rings that you see in Schwarzschild and also in Kerr, they are saddle points of this potential. This will be important later because generically that will not be the case. You can have light rings that are not saddle points of the potential. So, now with in mind the example that I gave in the beginning with one-dimensional potential that you could deform, and it was clear, I think, that if you make a deformation, a local deformation to create a new light ring, you have to create a second one. Can you wonder if there are some conservation laws for critical points? Of this two-dimensional potential. So this is going to be now the next step, is to discuss the topological charge of critical points. So for the moment, let's forget about light rings and black holes and spacetimes. Let's just focus on a two-dimensional space-like manifold, M and G, that has an orthogonal coordinate chart, X and Y, where the metric components of gxx is positive and gyy is positive. It's space-like, the signature. And it's orthogonal, so gxy is equal to 0. Then you can consider some real function. H, that depends on these two coordinates, which is simply, it takes the manifold M and returns a real number. And you want this function to be at least C1. So this function H can be almost anything. It can be in particular points on a hill. So, pode partilhar os slides outra vez? Pode partilhar os slides outra vez? Okay, thank you, obrigado. So, imagine that you have this situation. You have this two-dimensional manifold that is space-like, and it can represent points on a hill. It can be the situation that is depicted here. So, you are you are close to a hill, and on the left here you can see some contour lines of different points on the hill. And you can recognize here that you have a point in the middle where you have a local maximum. So this should be more or less familiar to you, these sort of plots. So imagine that you are on the side of the hill, and you can clearly see where you are standing if the hill is going up. So you draw a vector going in because the hill is going up. It's the gradient of your function. If you now move slightly to the side, you can see that your gradient has changed direction a little bit. And you can draw that change on that angle indicator there, let's see, over there. So the angle has changed in the positive direction. When drawn like this, it rotates in the positive direction. And if you continue doing so and start moving around the hill, never going through the top, always around the hill, you can see that angle is always changing in the positive direction. And so on, and so on. And so when you return to your original position, the vector gradient is the same. It's still the same, but this integrated angle, it is not. So you can kind of make this intuitive rule that if you have a maximum or a minimum inside your contour, this leads to a full turn in the positive sense of your vector field. So let's take a more challenging setup. So two hills connected with a saddle point. So this is, in a similar way, the contour lines for this configuration. So imagine that you first make a contour, make a path just around the saddle point. So this point over here. And now something different happens. When you go from point A to this point here, the vector changes in the negative sense. You can see this clearly from the angle indicator in the top. If you continue going around the path, the angle continues to move, but still in the negative direction. And so on, and so on. So when you return to your original position, the angle is again the same, but now you have a full negative turn of your vector field, not positive turn. And so you can make this kind of simple rule that you go around the saddle point, it leads to a -1 full turn of this vector field. What happens if you now make a path around the saddle point and the local maximum? Well, in this case, if you start moving, the angle indicator can start moving in the negative sense, and at some point it can change direction and even be positive, but when all is said and done, and you return to your original point, the direction is the same, but the integrated angle is also 0. And so you can establish this very simple rule that if you have a contour that goes around the saddle point and the local maximum or minimum of your potential, you have no full turns of your vector field. Ok, so pode parar para partilhar os slides, por favor? So this is just to give a motivation for what I'm going to do next. É uma partilha infinita. Então, so this was kind of an intuitive perspective, what I'm going to show next, which is I'm going to introduce this topological charge in a bit more precise way. Some technical, alguns problemas técnicos, não? Não dá para partilhar só a câmera? Ah, já está. Okay, thank you. Okay. So with that motivation, let's try to recover in a more precise way those rules that I just mentioned around the hill. So let's us define a field Vx and Vy, okay, in such a way that Vx is essentially the gradient in the radial direction of your potential, but with a certain normalization. You divide by the square root of gxx. And Vy is defined in a similar manner. So why choose this kind of weird normalization? The reason is that if you compute the norm of the gradient of h, this is explicitly xh. If you take these expressions, this is explicitly Vx squared, Vy squared. So these satisfy, when you define this V in this way, you have a Cartesian-like norm. And so you can introduce also an angle, omega, in the following way. You have Vx, which is V cosine of omega. So this V is just the norm, so kind of the modulus of this. Then you have also Vy, which is V sine of omega. You can safely do this because these two components satisfy a Cartesian-like normalization. Okay, I will stop in a minute. Okay. So if you draw in the diagram Vx and Vy and kind of force a vector V, this angle will be omega. So, if you now define a contour, you define a closed curve on this manifold M that is piecewise smooth, has a positive orientation, and is parameterized by a constant, by a real parameter. Let's make such a drawing of some positive oriented, so this is oriented in the positive sense, and it is parameterized by some parameter lambda, and it is piecewise smooth. So this is on your manifold M. So imagine that you have this point here in your contour. It's a point P. And you compute the value of your vector at this point. We have this vector V, which is Vx, Vy. And now you can make a very interesting mapping. You can take an auxiliary space M tilde. So this is your original manifold M. And you can consider this auxiliary space that is parameterized by Vx and Vy. And you can take this point P and map it to this manifold, to a point P tilde, according to the components Vx and Vy of the vector at that point. Here, this point here is the origin, where the field is 0. So you can write a map. You can consider this field V as a map from your point P in your original manifold to a point p tilde on your auxiliary manifold. And in particular, if you can do this for every point, at each point considering the value of the vector field at each point, you can map this curve C to an auxiliary curve in the other space. So you can take a map of C lambda to C tilde lambda. Yeah. Sorry about that. So this curve here, it is projected to some contour on this manifold M tilde, which is auxiliary. Now, the orientation does not need to be the same, can be quite different, but I just want to stress that there will be a mapping from this curve to this one. So, if you start on this point and you do a full circulation of your contour, when you return to the original point, the vector is the same. If you now look what happens here, if you do a full circulation, sorry, it should be the other way. If you do a full circulation and return to the same point, the angle, the integrated angle, is not necessarily the same. So, let me just write that down. That if you do a full circulation on your contour C lambda of d omega, this will be 2 pi omega. So it is not necessarily 0. It will be a multiple of 2 pi. I hope this is clear from this picture. So this omega here is it can be an integer that is positive or negative. It's not a real number. Well, it's a real number, but not fractional. So you might wonder what is the meaning of this number here. And since I'm out of time, I have to leave this for the part 2. Okay, thank you very much.
So thank you, Pedro, for the first lecture. And so since we are out of time, we have time for one question from online and one question local, right? So anyone online has a question for Pedro? So Crispino is asking people in chat. So Zeus raised his hand. So Zeus, can you hear us?
Hi, can you hear me?
Yeah.
Yes.
Right, sorry, because I was watching the short course on YouTube and that was a little bit of delay, so I didn't know that I was already could ask the question. So Pedro, thank you for this first part of the short course, and I was just curious about on the hypothesis that you did in the beginning of the lecture. Could you elaborate a little bit more on what is circularity? Because I think, if I remember correctly, I think you use asymptotic flatness and circularity imply the existence of the arc theta submanifold, right?
Mm-hmm. Yes.
Somehow I believe you have to use Frobenius' theorem to imply that, right? So I believe that is some relation with the Frobenius' theorem and circularity, but I don't know what circularity actually is. So if you could say a little bit more of that.
Yeah, so circularity has a definition that involves the Ricci tensor, and it's well, it's a little bit technical and not exactly elucidating, so that's why I haven't written it explicitly. But it essentially implies that if you, together with asymptotic flatness, that you have these two space that is orthogonal. But yeah, I don't have much more to say. It's kind of an expression. It's difficult, I guess, to give a very intuitive meaning to it beyond this existence of these two space orthogonal to the Killing symmetries in that particular case. But it's more like a more formal expression than, well, for this short course, I didn't want to write it explicitly.
Yeah, okay, I see. And this asymptotically flatness, I think I could imply the existence of this submanifold using another type of asymptotics, right? Or it's crucial to assume asymptotic flatness?
Well, asymptotic flatness is crucial to obtain some of these well-motivated coordinates, but I guess you could, as long as you assume some necessary conditions to have these coordinates very well defined, it is fine to have different asymptotics.
Okay.
But then you just need to be careful how to really motivate that you have these coordinates and they have a space that is orthogonal in general. It's just because of that. Okay. Afterwards, you also have these asymptotic flatness will also be important for these contour integrations because these will give a non-trivial boundary condition. But at this moment, it is important only to have this well-defined meaning of the coordinates.
Okay, okay, I see. Thank you.
Okay, thank you.
So thank you, Zeus, for the question. So anyone we have time for one question from the local audience. Caio, please.
So you are studying the basically characteristics related to null geodesics, right? So is there a way to investigate the importance of unstable circular time-like geodesics? For instance, in black holes, we always have these ISCOs. Mm-hmm. And for ultra-compact objects, you might have even orbits inside the star. So maybe there is something there that could be important, how this formalism could be applied to this case.
Thank you for your question, Caio. Indeed, there has been some papers in the literature about this, about applying some of these topological theorems and charges to time-like geodesics. Not exactly to ISCOs specifically, but you could do that, yes. And this can be generalized because this technique about topological charges, doesn't care about if it's null geodesics or not. So it's more general. So, and there have been some attempts to do this. Yes.
Yeah. So because Henrique, so since his question is a little bit interesting. So he asked why the potential has to be only dependent on R and theta instead of. So why should be independent of T and phi?
Okay, that's a good question. It's because you assume that you have two Killing symmetries. And because you have these Killing symmetries on the T and phi direction, the metric does not depend on those coordinates. So that is crucial. Otherwise, if you have a dynamical space-time, or you have a space-time that doesn't have axial symmetry, in general, you might not have even circularity, so you cannot make that the composition. So it gets much more trickier. But that is why.
So thank you. I think it was Henrique Vieira, which so he's thanking you from the chat.
Thank you.
So let's thank the speaker again for his very nice lecture.